So today, chapter 1, we're going to continue that. That was physical quantities and units. Okay, so last time हमने prefix table तक पढ़ा था, that how to add and how to remove a prefix. Now the next topic is the significant figures. The significant figures tell you the precision of an instrument. Now what is precision? Precision is the least count, that is the smallest division of an instrument. Like if we have a ruler, then the smallest division, the least that a ruler can count is its least count. And it's probably, you know that it's 0.1 centimeter. Similarly, vernier caliper has least count of 0.01 centimeter, and micrometer is more precise that it has least count of 0.001 centimeter. Okay, now how we're going to represent our answers in the paper? Like, it's usually in 2 decimal places. It's written in your exam, or you can say 3 significant figures. So now in significant figure, if we look at this table, the first number, that is 501, is written in 3 significant figure, which means that we have to count all the digits. If there is no decimal place, like there's no decimal place, then we have to count the whole number. That would be our significant figure, and we have to sometimes write it in standard form. Okay, similarly the second, that is, okay, 608,000, that in which we have 3 significant figure. Similarly, we look at this example, it has 1 significant. Similarly, if you look at the table, you'll get an idea that how we can represent the significant figures. Okay, then comes the concept of accuracy. Now what is accuracy? Accuracy is degree to which how much measured value is close to the true value. Like if we are measuring a value of g that is 9.8, we know that. But if we are doing an experiment, so the value of g would, and we get 8.9. So that is not accurate because it is not that much close to our true value. If we get a value of 9.7, that we can say is accurate. Okay, because it is close to our true value. So accuracy is how much your measured value is close to the true value. Okay, now it depends on 3 things: skills of an experimenter, equipment used, and technique. Okay, the more skillful an experimenter is, the more accurate value you would get. Similarly, equipment should be new, okay, and technique should be correct one. Then you will get an accurate value. Okay. Then we came across that precision. Precision is it is determined by the range of measured values. Okay, so we know we usually take multiple values, okay, to get an average answer. So if we take multiple values, so it shows that how much our values are close to each other, which means that if more range, then less precision. If your highest value is 9.8 and your lowest value is 7.5, then it is a precise. But if you get 9.8 and then you get 4.5, then this is imprecise because the range is very much large. So similarly, precision also depends upon multiple factors like significant figure, decimal points, and least count of instrument, that is micrometer. If we choose micrometer, that would be more precise, that would give you a more precise answer. So these precision depends on these 3 things. Okay. There's a point to note here that an instrument that is precise does not mean that it is accurate too. Okay, then if we are getting a micrometer reading of 4.5, that does not mean that it is accurate because G is always 9.8. If we are getting close to 9.8, then we can say it is accurate, else it would be not accurate. Okay, then we can see a table here which shows how the values are related to each other. So we are comparing 9.81, that is a value of G. Okay, in the first row we can see that most the values are uh, close to the true value as well as they are precise. Okay, the highest value we have 9.81 and lowest one is 9. So there is a uh, 0.2 difference between the values range. So this means that the row is accurate as well as precise. On the other hand, if you came across the second row, you can see that it has a very different values, okay, apart from 9. Although it does contain 9.81, so we can say the result is accurate, but that is not precise because the lowest value is this and highest is this, which makes the range very much large. So this experiment is imprecise. On the third row, we can see that result is inaccurate. Not a single value is 9.8. So that would be an inaccurate result. And but on the other hand, it is an precise. Why is precise? Because the range is less. Okay, that is very short range. And the last row, we can see that neither it is accurate nor precise. Okay, so both conditions fail here. So in this way, you can analyze the values and judge whether it's accurate or precise result. Now we can also analyze these accuracy and precision through graphs. This is a graph of number of readings on one hand and readings that is being taken on the x-axis. Okay, then the first graph we can see that there's a huge peak at the true value. This is your true value, which means that most of our values lie on true value. Okay, which indicates that our experiment is accurate. To check precision, we can analyze the range. You can see that range is less, which means that result is also precise. Moving on to a second graph, we can see that most of the values are not a single value is on the true value, okay, which means that the result is inaccurate. Similarly, the experiment is precise because the range is less. Then moving on to the third graph, which means shows that the result is accurate. Okay, there's a peak on the true value, but the range is very large, which means that the result is experiment was imprecise. Then our fourth graph shows that the result is neither accurate nor precise. Okay, because it is not on the true value and the range is also very large. In this way, you can analyze the precision accuracy through graphs also. Okay, then there is a concept of errors. Error, what is error? Error is the difference between the measured and the true value. Okay, simple definition, it is that difference between measured and true value. Now, what are the sources of errors? There are two sources. Number one is a random error. Random error, by definition, you can see it is written errors in measurement that lead to mean values when the same measurement is repeated, which means that the values get inconsistent when the same measurement is repeated. What are the sources of this error? Sources of random errors are due to the factor that are not in human being. that are not in control of human being, those lead to the sources lead to random errors. Like we can say any natural factor, okay? We can say the wind, okay? That would affect uh, random error. Similarly, these error can be now how we can reduce, okay? That is a very important point. We can reduce these errors through repeating the experiment and taking average of measured value. This thing is repeatedly asked in your exams, that what can be done to reduce random errors. So this is the solution of reducing random errors. Okay, now we need to see the relation. Random error increases the range. Now I have previously told you that range is related to what? Precision. So higher range means less precision, that your data will be less precise. You need to remember this. Okay, so random error lead to precision. It is written over here. Large random error equal to high imprecision. You need to remember this rule, this relation also. Okay, so how to overcome that? We draw a graph and then we draw the line of best fit. So these are multiple inconsistent values. Okay, what we can do, we can just draw a line of best fit. Okay, and then we can find the results. That is the only solution to solve a random. Second is your systematic errors. Systematic errors occur when that there is a fault in device or system or the procedure that is being used. Three things. It can be fault in any one of these. That is called the systematic error. Okay, it cannot be eliminated by repetition on average. Okay, if you're repeating the same thing with a faulty device, that would not result in an accurate thing. Okay. Similarly, second point is errors due to wrong calibration or zero errors. Okay, or type. Same thing that you are using the device wrongly, that means like wrong calibration or zero error in vernier caliper or micrometer leads to systematic error. If a graph has an intercept, then it shows systematic error. How you can identify systematic error? If there is a y-intercept in that graph, this shows a systematic error. Okay, I hope you got the concept of random error and systematic error. The concept of uncertainty. Uncertainty is the range within which the true value is likely to lie. Okay, you are given a range within which a true value is likely to lie. Like it, if there is a 50, okay, mass is given with an uncertain, which means that it could be around 49 to 51 in between these two values. So that is what an uncertainty, that you are uncertain about a value. So you give a range of that value. So you need to remember these three terms. That is, number one is absolute uncertainty. We write it like this: delta, then the quantity like mass or V, okay, or Q, anything else. Then we have fractional uncertainty. Say that is comes as a fraction, okay, like this. Then third, you have percentage uncertainty. Then you divide this by 100%. Okay, that would give you a percentage uncertainty. Note that uncertainties are always added. Okay, no matter what, they are always added. There is no subtraction in uncertainty or multiplication or division. They are always added. Whether they are fractional, whether they are absolute or percentage uncertainty. So we can take an example of this. V is equal to d upon time. Okay, that is velocity equal to distance. So I'm doing the, okay, these are the fractional uncertainties and I'm adding these. Okay, similarly, density is mass upon volume. So I'm adding the fractional uncertainties. So similarly, if we look at this example, okay, L is this and this, okay, this is your delta L and this is your L, okay. So absolute uncertainty is zero point 0.4 centimeter. Fractional uncertainty, you can calculate it by dividing it with 28.3, that will give you. And if you want to find percentage uncertainty, you can multiply it by 100%. That will give you percentage uncertainty. This is how you commute different uncertainties. Now, this is an important concept, okay, that you need to get whenever the equation is, there's no fraction in that equation, okay, only addition or subtraction is being done, okay, in the equation. You just need to add the absolute uncertainties. There is no fraction, okay. Similarly, you can see in this I have also added, with this I have also added. You need to remember this concept. Then we have the fourth. In this, we are multiplying the two quantities. Now we have to use fractional uncertainties. You can see. Okay. Now comes the fractional uncertainty. Similarly, if we are dividing, then we have to use fractional uncertainties. Okay, we can see in the example 6, we are again implementing the same thing. Okay, but in 7, there is an exponent power on A. So what you're gonna do is place it at the front and multiply it with the whole uncertainty fractional. That is how you're going to commute this. Okay, like if this power square, then you're going to use this. This is how it's going to be worked. Similarly, you can see example 8. We are going to multiply the half with whole fractional uncertainty. So you need to remember these rules. Okay. Then we have a question solved here, that is Ti, initial temperature with its uncertainty and all. Then Tf, that is final temperature with its. We need to find delta T with uncertainty. Delta T is change in uncertainty. The change in uncertainty would be calculated. The change in temperature would be calculated as, okay, 16 minus 25. That would result in 35. Then what we need to find the uncertainty in that change. Okay, and we know that uncertainty is always added, so we're going to add the both. That is our uncertainty change. So that is all for the uncertainties concept. Next video we're going to look at the vectors and how we're going to resolve the two-dimensional vectors.